Today's topic is ions in aqueous solutions and net ionic equations. We've mentioned before that ionic compounds, they dissociate into their ions in solution or in aqueous solution. So we're going to kind of investigate a little bit more into this in terms of what ionic compounds dissociate, and maybe some do not, and if they do dissociate, how many ions they produce, and how all this comes together in terms of chemistry and chemical reaction equations with net ionic equations. This is one of my most favorite little cartoons. If you're not part of the solution, you are part of the precipitate. Okay, a little preview for what is to come here. All right, ions in aqueous solutions. Most ionic compounds are soluble. Let's time out here. Soluble means you can mix well and dissolve evenly in water's solvent. So most ionic compounds are soluble in water because they dissociate into ions, meaning the positive and negative ions that exist in ionic structures are actually broken apart and surrounded by my polar water molecules. Last time we talked about each water molecule itself contains a partial positive charge and a partial negative charge, which means ionic compounds are actually going to exist as ions in aqueous solutions and can be expressed with a dissociation equation. A dissociation equation is kind of modeled for you down here, okay? It is me showing that solid ionic compound, what it looks like when it dissociates or breaks apart into ions in solution. So what I'm looking here is taking solid sodium chloride, and once it is put in water, I would designate that it breaks up into the ions of the sodium ion and of the chloride ion, both of those in water, which is why I represent them with an aqueous or AQ symbol after that. Okay, so we got to get used to seeing whenever I write the symbol for an ionic compound with an AQ at the end, the understanding behind that is that that sodium chloride is not just stuck together as that formula unit in that crystal lattice, okay? That AQ tells me that what we're really looking at here is the sodium and chloride ions separately, just existing together in that aqueous solution. So I thought we would practice writing some dissociation equations, because that's kind of a new fun thing that we've learned today. So I have 3 examples here. What I want for you to do is we're going to name what each one of these compounds are. You're like, oh my gosh, the naming, the nomenclature. Y'all, this is never going to go away. Yes, we're going to name these things. And then we're going to write that dissociation equation showing that substance breaking apart into ions and how many ions it actually breaks apart into. So yes, this is an ionic compound, magnesium and fluorine, or magnesium fluoride. So magnesium fluoride. Okay, remember when I'm naming ionic compounds, there's no need to tell me how many fluorines you have. I know that magnesium's got a +2 charge, right? Because he is an alkaline earth metal. So everybody in that group makes a +2 charge. And fluorine is in group 17. He's a halogen, which means he will make a -1 charge. So to make a neutral formula unit between something with a +2 and something with a plus or -1, I've got to have 2 of the fluorides. That was a little bit of a tangent, but that is not as much. That's kind of the minimum amount of review that I feel like I really want to do on nomenclature today. If you're still struggling, we got lots of previous video lessons for you to practice and tackle that. Okay, so this is magnesium fluoride. It's an ionic compound. It's going to dissociate in water, okay? So I'm going to write the dissociation equation. I have magnesium fluoride, and it is going to break apart. We mentioned that magnesium, because he is group 2, he's got a +2 charge as an ion. So the magnesium ion will look like Mg +2. I only have 1 of him, which is why I only represent 1 of those magnesium ions in my dissociation equation. Now I have a second type of ion. That is a fluoride ion. But look at that subscript. How many fluoride ions am I going to make? 2. So I would write 2F. And this is the ion, so fluorine as a halogen is a -1 charge, so I would write minus. So this is showing that 1 magnesium ion breaking apart with a +2 charge, and the 2 fluoride ions with a -1 charge, also dissociation. This is dissociation, those ions separating from each other. So now it says, well, how many total ions are going to be there in the water environment? Well, I have 1 magnesium, and I have 2 fluorines. How many total is that we can add? Yay, 3 total ions in solution. Okay, next one is I have, let's see, when we name ionic compounds, we name the 2 things that we see. We have sodium and we have sulfate polyatomic ion. So we're going to call this sodium sulfate, okay? Sodium sulfate breaks apart into ions, so I'm going to write a dissociation equation for him. So Na2SO4, and if you want, you can totally keep your polyatomics in parentheses. I love to do that. It makes me feel better. So the sodium ion comes first. I have 2 of him. What charge does the sodium ion have? He is a group 1, so he makes a +1 charge. So I have 2 sodium ions. And then I have 1 total of these sulfates. There's nothing on the outside of the parentheses telling me I have more than 1 of that polyatomic. So I have SO4. And what is the charge of a sulfate polyatomic from my list of my polyatomics? He's got a -2 charge. Okay? So I have 2 sodium ions plus 1 sulfate ion. How many total ions? I have 3 of them. Cool. My last one, oh my gosh, what is going on here? I just still have 2 things in an ionic compound, that guy and that guy. Well, that guy is a polyatomic. He is ammonium. That guy is another polyatomic. He is phosphate, yes? So this is just ammonium phosphate. Ammonium phosphate. Ooh, the dissociation equation for this is going to be a little bit big. I'll see if I can write kind of small, see if we can execute this. So I have ammonium phosphate. He is NH4 with a 3 on the outside. That means I'm probably going to have 3 of him, right? And then PO4. Looks like I have only 1 of them. Let's see how this works out. So yes, my first ion is the ammonium ion. Each one has a +1 charge that I've shown here before on the list of polyatomic ions. And it looks like I have 3 of them. So I have 3 NH4 plus. And then the next ion I have is the phosphate ion, right? And I only have 1 total of those PO4 ions. So PO4, and it is a -3 charge. So as a review, my phosphate has a -3 charge, okay? So I have 3 ammonium ions. I have 1 phosphate ion, so that gives me a total of 4 ions that will be dissociated for ammonium phosphate when it gets into aqueous solution. So these are dissociation equations. It basically just shows what is going on when I take any one of these soluble ionic compounds and put them into water, okay? So now this begs the question of like, are all ionic compounds, do all of them do this? I don't know. Let's see. Well, some ionic compounds are insoluble in water. You're like, what the meaning they don't dissociate into ions. We check what is called the list of the solubility rules to determine if an ionic compound is soluble or insoluble in water. If an ionic compound is not soluble in water, it will not dissociate into ions, and therefore it will not dissolve, and it will instead sink to the bottom of the solution no matter how much stirring or agitation or heating up I do. So for an example, silver chloride is actually an insoluble ionic compound, to where if I were to put it in water to try to make an aqueous solution, it's like, no thank you, I'm not going to break apart, you guys, to where there's like not even a dissociation equation because it doesn't dissociate into ions. It's just going to stay to the bottom of the beaker still as its solid crystal lattice representation. So visually what that would look like if I tried to put silver chloride in water, it will not dissolve. It will fall straight to the bottom no matter how much stirring I do. So you're like, what do you mean by the solubility rules? We have these as a list on the back of our reference chart, okay? The way that I read this is I think about my solubility rules chart as like a beaker, okay? Where this bottom category represents something that would be falling down to the bottom, meaning something that will not dissolve or mix evenly within my water. It's going to be insoluble. So this category is my insoluble ionic compounds, the ones that will not dissolve, will not dissociate into ions, the ones like my silver chloride, okay? Now up here at the top of the beaker, I think, okay, if I'm up here at the top, I'm like in the water solution, I'm mixing, yes, I'm soluble in that water. I will dissolve and I will dissociate in ions. So these guys actually exist as ions in an aqueous solution, not stuck to the bottom as a solid. Okay, so here's some examples of various ionic compounds. I noticed these first 4, I have nickel 2 chloride, potassium permanganate, copper 2 sulfate, and lead 2 nitrate. They look like homogeneous and evenly spread throughout. Yeah, we would say that those specific solutes, these specific ionic compounds, are soluble in water, and looks like they are mixed evenly, which means I know that these actually exist as ions in that aqueous solution. But these two guys over here, I can see a clear separation of where the ionic compound is, and then where the water environment is above. So these would be called insoluble ionic compounds. So I can see that. So now let's practice using our solubility rules and see if we can determine, first of all, if these ionic compounds are soluble or insoluble. And then if they are soluble, we can practice again writing some of these fun dissociation equations. Okay, so I've got my solubility rules handy. I'm really excited about that. Let's see. Oh, more naming. That's okay. No matter if they are soluble or insoluble, if you are an ionic compound, I would expect for you to give me a name of these ionic compounds. That is barium and that is chlorine. No weird polyatomics. Barium chloride is what we have here. And in fact, if we want to just go ahead and name all of these, I think it may be a good idea. That way we're in our nomenclature brain and don't have to do any freaky stuff hanging out here, okay? I'm actually going to do this one last. I almost said the name. We're going to do this one last. I'm going to jump down here to this guy. I have aluminum as my cation, and I have the nitrate polyatomic ion as my anion. So this is aluminum nitrate. This one down here, as I have magnesium as my cation and hydroxide as my polyatomic anion. So this is magnesium hydroxide. So once again, with naming an ionic compound, you just name the two things you see. You do not care about subscripts unless you are dealing with somebody here that is not a group 1 metal, a group 2 metal, or my little combo arrow of silver, zinc, and aluminum. Okay, silver always has a +1, zinc always has a +2, aluminum always has a +3. Everybody in group 1 always has a +1 charge. Everybody in group 2 always has a +2 charge. Where things get a little bit weird and hairy is down here in this transition metal area, meaning everything to the right of my group 2 guys, including when I get to the staircase. These guys have a variable possibilities of oxidation numbers or charges that they can make. Okay, so with that being said, I knew aluminum, he's always going to have a +3 charge. There was no need for me to even think about that. Same thing with magnesium. He's always going to have a +2 charge. There is no need for me to think about that. I think I said aluminum had +2, +3 for aluminum, right? Now on this one, oh, I was even looking at that one wrong. I thought this one was SN for lead, which SN totally would be one of those weird transition metals, but this is actually nothing to worry about. This is just SR, which is strontium, a group 2 metal. So I don't even have to think about that. It is just strontium, and then that polyatomic ion is sulfate. Strontium sulfate. So sorry about that if I freaked y'all out. But keeping with that train of thought on what I was even kind of trying to play out here with y'all, is that if I have one of these transitioning metals that are underneath the staircase, not group 1 or group 2 or silver, zinc, or aluminum, I have to specify what charge that metal has by a Roman numeral in parentheses, okay? So we will have some problems like that here a little bit further on down. Okay, but now I'm going to practice using my solubility rules to see if each one of these guys are soluble or insoluble. And the way I do this is I look at the last part, or the anion, and try to match and find where that anion for the compound is on here. And then I can kind of check and see if it's an exception or not, and then classify whether it's soluble or insoluble. Okay, so my first one here, barium chloride. Chloride. I'm going to look for chloride. You were like, chloride. Just not say chloride. Well, chlorine is a halogen. Everybody in group 17 is a halogen. So chlorine and fluorine and bromine and iron, all of these are actually what we call halides. So a halide is a way to express a halogen ion. So barium chloride is a halide. Well, is barium an exception? No, I do not see barium as an exception. That means barium halide is going to continue to be in the category which it was originally placed under. So barium chloride is soluble. Which means what to me? Are soluble ionic compounds, do they get to dissociate in water into ions? Yes. Insoluble is the ones that do not. So can I write a dissociation equation for barium chloride? I can. He's soluble in water. So just like we did before, he's going to break up into ions. Barium is group 2, right? Where's barium? Yeah, group 2. So he's +2 charge. There was only one of those bariums. And then chlorine, chloride, there are 2 of them, is Cl, and each Cl ion has a -1 charge. There's 1 barium ion and 2 chloride ions. There's 3 total ions that barium chloride dissociates into. Next one is we have strontium sulfate, sulfate. The ending guy is sulfate. We're very excited about that. Sulfate. But boom. Cool. All right, he's soluble too. We're going to write soluble. No, check the list of the exceptions. We had strontium sulfate. Strontium is an exception. What this means is that most sulfates are totally soluble. Most sulfates will dissociate into ions. I can write a dissociation equation, except for the ones that are paired up with these specific metal cations. Strontium, when it's paired up with sulfate, it is not soluble. So if you are an exception, that just means whatever category you were originally listed in, you are now in the opposite category. Okay, so exceptions to being soluble means that I am insoluble. Oh no, that is annoying. But you know what's not annoying? If I'm insoluble, I don't even have to write a dissociation equation. So like, whew, thank goodness. Because insoluble ionic compounds do not dissociate in an aqueous solution. Next one is I have aluminum nitrate. Soluble. And there are no exceptions. I don't even have to think. All nitrates are soluble, so I get to write soluble, which means if it's soluble, I get to write the dissociation equation, right? Aluminum nitrate breaks apart into 1 aluminum ion. Aluminum always has a +3. And 3 total nitrates. 3 NO3, and each nitrate, as a review, has a charge of, there we go, -1 charge. Okay. And last one, magnesium hydroxides. I searched for hydroxides. Oh, it's down here on the very, very bottom. Okay, well, is magnesium an exception? Group 1 cations. Magnesium's group 2, so that does not apply. Nope. Magnesium hydroxide, not an exception, so he stays here. He's truly insoluble. Does not break apart into ions, which means I have no dissociation equation for magnesium hydroxide, which is really cool. Okay, so now that was a great lesson on seeing how things dissociate, and we know that dissociation is going to determine, or is going to be determined by whether the compound is soluble or insoluble according to my solubility rules. So what does this mean in terms of chemical reactions with some of these aqueous solutions of ionic compounds? Well, we have these types of reactions called precipitation reactions. We've actually kind of learned these before, and we've even written these chemical equations before, so thank goodness this is going to be kind of a review for us. It says, in a chemical reaction between 2 aqueous solutions of ionic compounds, a double replacement reaction occurs, where I have the couples swap partners to make 2 new couples. And what ends up happening is this result is going to be one product being soluble, which means aqueous, and the other one being insoluble, which means it will be a solid, not dissociated in ions. The insoluble product is known as a precipitate, which is why we call these specific double replacement reactions as precipitation reactions. So a precipitate is the insoluble product. If my solubility rules classified something as insoluble, we know that that specific product would not dissociate into ions, and it would be solid, clearly making something weird and freaky that would eventually fall down to the bottom of the beaker outside of your aqueous solution. Okay, so we talked about our solubility rules in terms of soluble being up top, insoluble being on the bottom. Well, in terms of these chemical reactions, I can say that, yeah, my soluble products are going to be ions, so they will be technically classified or labeled as AQ, aqueous. Remember we said if something is labeled as aqueous, it is assumed that we know that it is actually in ions in solution. Now my insoluble stuff as a product of a precipitation reaction is going to be labeled as an S, meaning it is not dissociated, it is stuck together as that ionic crystal lattice structure, not dissociated into ions. So let's see if we can maybe do a first practice problem here on practicing writing these double replacement reactions with two aqueous solutions of ionic compounds. It says aqueous solutions of ammonium sulfide and cadmium 2 nitrate are combined. Well, here's the trick about this. I could look up ammonium sulfide and cadmium 2 nitrate on my solubility rules. Both of them would be soluble, but I also told you if I'm starting you off with aqueous solutions of these things, it is assumed that, well, yeah, in order to have an aqueous solution, yeah, they're going to be soluble on your solubility rules. So I don't have to check my reactants, which is always good. They're always aqueous. But what is sneaky is that I have to write a formula for these, which means I have to do a crisscross, right? Ammonium is the polyatomic ion NH4 with a +1 charge, right? Cadmium 2 sulfide is sulfur as an ion. Now, sulfur as an ion is group 16. Everybody in group 16 has a -2 charge. So these are the two ions that come together to make ammonium sulfide. Making sure that I have a neutralization of charge, I must have two ammoniums to cancel out one sulfide. Okay, I need two of the +1 charge guys to cancel out one of the -2 charge guys. So this is what I say when I say crisscross. We take those numerical values of those charges and we put them down as subscripts on the opposite ion. So I have NH4, and we said we had two of them, and we only have one sulfur, okay? I'm going to put a little spot here for me to balance because I'm going to assemble a chemical reaction equation. I'm going to have to remember to put a coefficient in there or else none of it makes sense, right? Okay, next guy is that I have cadmium 2 nitrate. Well, here's a Roman numeral. What is even going on with that? Well, cadmium is a transition metal. That 2 represents that specific metal. Cation has a +2 charge, okay? So cadmium with a +2 charge. Thank you for letting me know, because cadmium on my transition metal chart, I'm like, y'all, he's not in a group that I know what his charge is. I have to specify. And then nitrate is the polyatomic ion NO3. Collectively, that entire thing has a -1 charge. So the ratio of ions of a cadmium and a nitrate that I need to balance and neutral the charge is going to be 1 cadmium, so we would say CD, and then 2 nitrates, so NO3, 2, with the 2 on the outside. Okay, and I can go back, since these are both aqueous solutions. I should have done this, sorry you guys. I can write that this was aqueous and that this was also aqueous. Okay, making sure we remember whenever I say a ionic compound is aqueous, that's really just, they're actually existing as ions in solution, which we won't get to what that, maps out to look like here in a little bit. Okay, so we double replacement reactions, which means these guys swap partners. The ammonium metal cation is going to pair up with the anion from the opposite compound. If there are any subscripts from their previous reactant situation, we get rid of those and we create a brand new crisscross from the ions from scratch. Okay, so what that means is my first compound of ammonium and nitrate, each one of those ions has a charge of a 1, a +1, and a -1. So it's going to be a 1-to-1 ratio. So we would write NH4 and then NH3. I like to keep my polyatomics in parentheses, even if I only have one of them, because it's going to make things easier to balance here in the end. So my second compound is going to be between the cadmium cation and the sulfide anion. We always write the positive metal cation first, and then the negative non-metal anion second, okay? Looking at the charges, right, of each one of those, each one of these guys, cadmium has a +2, sulfide has a -2, it'll be a 1-to-1 ratio to neutralize that charge. So I have C, D, S. Okay, now I'm going to balance, because I'm like, oh my gosh, I'm ready to balance, but then I have to look at my solubility rules and figure out, well, who's soluble and insoluble and all that fun stuff. So for balancing here, it looks like I have 2 ammoniums on this side and only 1 on this side, so I got to put a 2 here, and that balances my ammoniums. But now it gave me 2 nitrates, like, oh my gosh, that's okay, I have 2 nitrates on there. Looks like everybody else looks to be balanced to me. Awesome. Now I just need to check the solubility rules and see if ammonium nitrate is soluble or insoluble, and what does that mean in terms of labeling him. Oh, it's a nitrate. Y'all, all nitrates are soluble. This guy is totally going to be aqueous. Now cadmium 2 sulfide, 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 sulfide. Whoa, okay. It looks like he's insoluble, and y'all, cadmium is not an exception to that rule. So insoluble products of these precipitation reactions are solid. So this guy right here is actually going to be my precipitate, and precipitate abbreviation is PPT, like PowerPoint. Like I just do not know. That is just wackadoo. Okay, so looking at this here, if I were to perform this chemical reaction, this is what I would see. I would see some shocking precipitate being formed from two like clear aqueous looking solutions. So that is what the precipitate for cadmium 2 sulfide actually looks like, which is really cool. So here's me mixing two aqueous solutions of these specific ions in water, coming together to make one soluble product that exists as ions in solution, and one insoluble product that exists stuck down to the bottom, staying away from all those water molecules in solution. Okay, so let's do one more of these, practicing writing double replacement precipitation reactions, okay? This one says a solution of silver nitrate is mixed with a solution of sodium chromate. Okay, silver nitrate. Silver is always a +1 charge. Nitrate polyatomic is a -1. So the formula for silver nitrate is AgNO3. I have a 1-to-1 ratio. It's also a solution, which means I know that this is aqueous. Mixed with a solution of sodium chromate. Sodium is a +1 guy. Chromate is a polyatomic ion, I'm pretty sure. We typically don't use chromate that much, at least in our 10th grade chemistry class, but he's CrO4 overall with a -2 charge. So we would say CrO4 with a -2 charge. So it looks like I'm going to need 2 sodiums to neutralize one of those chromates. And this is aqueous. We said we got an aqueous solution. All right, swapping partners. The positive guy goes with the other negative guy. That positive guy goes with the other negative guy. Drop subscripts, make a crisscross from scratch, figuring out what the ratio of ions you need. Silver, we said, was +1. Chromate is -2. So that means we have 2 silvers to neutralize that 1 chromate, okay? I'm going to pause and fill in what version it is with my solubility rules, but while I'm cranking on here, completing this reaction, I want to continue that train of thought. So then my second compound is between sodium and nitrate. Well, sodium, I do not care. He had a 2 when he was with chromate. He's not going to be with chromate anymore. He's going to be with nitrate. We're going to make a new subscript situation. Sodium's +1, nitrate is -1. So my formula for sodium nitrate is going to be NaNO3, and I only have one of them, okay? Let's balance and get that out of the way because we know that is important. It looks like I've got 2 sodiums over here and only 1 over here, which means I'll need to put a gaga in front of sodium nitrate. That gives me 2 nitrates over here. Well, then I need 2 nitrates over here, which means I put a 2 in front of there, which gives me 2 silvers over here, which means I need, we good now. Amazing. Okay, let's zone in on these products and figure out who is soluble, who is not, what is going on here. So I have silver chromate. So I'm looking for chromate, 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 chromate. Ooh, chromate is insoluble. Is silver an exception? No. This is my insoluble product. This is going to be my precipitate. But to double check, let's make sure that this guy is aqueous or soluble. Sodium nitrate, y'all, nitrates are always soluble. No big deal here. Sodium nitrate is going to exist as ions in solution. He is aqueous. Okay, so this guy is the precipitate for this reaction. And if I were to visualize what would happen when I would actually be doing this chemical reaction, would see something like this, okay? I would see this crazy, like burnt, rusty red color of a silver chromate precipitate out of solution, which is really, really, really cool. Okay, so once again, I'm mixing 2 aqueous solutions, meaning stuff that is already ions dissolved in water, combining them. One of the products stays dissolved as ions in water, and the other product that's being formed creates a solid precipitate that sinks to the bottom and is usually a really fun, crazy looking color. Okay. So what does this all mean if I kind of bring it all together? This is bringing us to the term net ionic equations. So there are actually several ways to write chemical reactions in aqueous solutions, depending on the information you want to get across. They include just a balanced molecular equation, like we practiced writing just now, okay? Then a complete ionic equation and then a net ionic equation. I have kind of a situation here down here, blah, 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 blah. We're going to walk through an example of going from a balanced molecular to a complete ionic to a final net ionic equation, step by step, okay? Now, the balanced molecular equation gives an overview of the compounds that are involved in the chemical reaction. The BME shows the reactants and the products in their combined form, and usually, includes the state of matter like solid, liquid, gas, or aqueous. And it's the whole thing is going to be balanced, okay? These are full double replacement reactions that we've been able to write and balance since December. We just now know that that's complete balanced molecular equation. But we now know these aqueous ionic compounds are technically not like that in solution. If I'm telling you it's aqueous, they're actually separated as ions, which means I can do all of this. You're like, what is even going on here? So when we create these aqueous solutions, dissolved ionic compounds, the compounds are floating around in ion form rather than the complete formula unit. So my complete ionic equation designates the compounds as they would actually behave in solution. So that would require any soluble or aqueous ionic compound or strong acid to be written as ions, including their charges. Precipitates are only written as the ones that are combined. You were like, what is even happening here? Well, remember when we practiced writing those little dissociation equations where we took one soluble ionic compound and we showed what ions it broke up into? That's basically what we're doing here, starting from my balanced molecular equation. Each one of these guys, we've basically expanded them out or showed that dissociation into what ions it produced. So we did that for everybody here, except the only one we did not do it for is my precipitate, my solid, the one that does not dissociate. So, oh my gosh, that is very long. I agree, which is why we bring it down to the net ionic equation. The net ionic equation describes the actual chemical reaction. So here's the trippy part. Like, there's a lot of people in this double replacement swapping situation here. But the reaction actually only involves the particles which undergo a change in some way, okay? To write the net ionic equation, I can remove the particles which are the same on both sides of the equation, both in type, meaning what the substance is, and in quantity, or the number of that. Those ions are called spectator ions. The remaining particles gives the overall net ionic equation. So this is that ginormously long, complete ionic equation that we wrote of everybody breaking apart into ions. But if you'll notice, I have 2 nitrates on the reactant side and 2 nitrates on the product side. Those cancel each other out. And then I also have 2 sodium ions on the reactant side and 2 on the product. They're exactly the same. They cancel each other out. So the sodium ion and the nitrate ions are spectator ions. They look the same before the reaction, and after that, they're just hanging out in solution, watching whatever's happening down below happen. They're spectators. Okay, the remaining particles here give the net ionic equation. This is the only chemistry being done here with this crazy wackadoo, lots of people playing, swapping partners. Just this, me taking a silver ion or 2 silver ions and a chromate ion dissolved in water and saying, now y'all come together and create a solid precipitate. That is all that is really happening here in these precipitation reactions, which is why the net ionic equation is useful, because it tells us like the true story of what is actually important in terms of the chemistry. So now we're going to practice writing these double replacement reactions, which we now know that is the balanced molecular equation, and we're going to scaffold it down to create the dissociation of ions with the complete ionic equation, and then canceling off spectator ions for my net ionic equation. Okay, so now I'm going to go a little bit quicker on assembling my double replacement reaction, meaning my balanced molecular equation, and not talking too much about like forming the charges and the whatevers and to make the compounds, so we can get down to the more challenging stuff of the complete ionic and the net ionic. Okay, so solutions of ammonium sulfate. Ammonium's +1, sulfate's -2. So I have NH4, 2 of them, and I have 1 sulfate, SO4, 1 of them. Okay, and this is an aqueous solution. My second reactant is lead 2, so this lead has a +2 charge. Nitrate always has a -1 charge, and so I would have PbNO3, 2. Okay, So swapping partners here means that ammonium pairs up with nitrate. Each one of these has a charge of a 1 magnitude, to where I have NH4 and then NO3. Okay, well, first of all, I should have put that as an aqueous, right? I'm going to come back to what state that is, whether soluble or insoluble or aqueous or solid. I'm going to finish my double replacement reaction with lead 2 being paired up with sulfate, charges of 2s, which means you have one of each for that ratio. So I have PbSO4. Okay, so we're going to go ahead and balance this first, just so we can have all that committed down, right? So for the balancing of it all, it looks like I have 2 ammoniums here and only 1 over here. Well, we're going to put 2 here. Well, that changes 2 nitrates. Well, everybody good. Okay, which one is soluble? Which one is insoluble? Nitrates are always soluble, so this guy is still aqueous. And lead 2 sulfates. Let's check, hopefully. Well, he's soluble too, but oh goodness, is lead 2 an exception? Yes, so this will be my solid precipitate. Okay, so we've got my balanced molecular equation. So now what I'm going to do is each one of these aqueous guys, I'm going to write them as their separated ions, okay? Which means over here I have 2 sodium ions, or ammonium ions, and I have 1 sulfate ion, okay? So if we were to look at this, this is like a dissociation equation showing that separate into that. That's the dissociation that I'm looking at here. Okay, now moving on to my next guy. He dissociates, so I'm going to write his ions. I have a lead with a +2, only 1 of him. And it looks like I have 2 nitrates with a -1. Yes, so that's me showing this. Now I'm moving over to my product side. The first one we said dissociates into ions, yes? So I have 2 ammoniums, yes? And that coefficient gets distributed to everybody, so I also have 2 nitrate ions. Okay, so that was that happening here. And then finally, I have oh, do I break them apart? I do not. That's my precipitate. It stays together. So PbSO4. Okay, now what do I do? So here's my complete ionic equation. It shows all the dissociation. Now I'm going to look for what is the same on both sides and cancel them off. They will be my spectator ions. It looks like I have 2 ammoniums the same on both sides. And I have 2 nitrates the same on both sides. Those are my spectators. Everything that is remaining is showing the net ionic equation, what the actual chemistry is that is going on here in this chemical reaction. I have 1 sulfate ion combining together with 1 lead 2 ion to create lead 2 sulfate precipitate. Okay, so that's the actual only chemistry that's going on here. Okay, so let's do example 2. So this, once again, we just write our normal double replacement as normal, figure out what our products are, which one's the precipitate, dissociate everybody else except for my precipitate, and then cancel off your spectator ions, leading to who your net ionic equation is. All right, solutions of sodium chloride and silver nitrate are combined. So sodium's +1 charge, chlorine is a -1 charge. This is NaCl, you guys, not too scary. And it is a solution of him, so he is aqueous. And then I have silver. Silver always has a +1 charge. Nitrate has a -1 charge. So AgNO3, aqueous. They're going to swap partners. The cool thing about this one is everybody got charges of 1. So you, thank goodness, sometimes our brain doesn't have to think too hard, which we are grateful. But sodium does pair up with nitrate. And then I have silver pairing up with chloride. Ratios of a 1-to-1 for all of those ions. Sodium nitrate. Nitrate, are you soluble? Not all nitrates are soluble. So yes, this one is aqueous. And then silver chloride. Oh, I hope he's insoluble, or else we don't got a precipitate. Yep. Let's see. So we have, well, it's a halide. We said chlorides are halides, and they're soluble, but silver, any silver halide is going to be insoluble. So this is actually our precipitate. So that's our balanced molecular equation. Well, first of all, is it balanced? I kind of glossed over that, but yes, I have 1 of every single one of those, so it is balanced. Now for my complete ionic equation, blast apart all of the aqueous guys into ions. So I have 1 sodium ion and 1 chloride ion, and then I have 1 silver ion and 1 nitrate ion. And then on my product side, the only one that ionizes is the sodium nitrate, where I have 1 sodium ion and 1 nitrate ion. and then my silver chloride stays together as my precipitate, canceling off my spectators of sodium and nitrate on both sides. I have my net ionic equation just as chloride ion combining with the silver ion to make silver chloride. Okay, and a lot of kids are like, "Ooh, why you write the anion first?" Well, when they're separated as separated ion or ion reactants, it doesn't matter what order you like. If you want to write the silver ion first, like, that is super fine. I kind of understand that level of attention to detail and wanting the universe to like kind of look the same and stuff. But one thing I want to talk about is like what this means in terms. She's like, well, the net ionic, you're saying that the only chemistry that's happening in here is the silver chloride being formed, and everybody else is like a spectator here. Okay, so I love these particle diagrams. These particle drawings really kind of help visualize, oh, I see kind of what's happening here in these aqueous solutions here. Okay, so here was my original first reactant of sodium chloride. And here was my original first reactant of silver nitrate. You can see the sodium ions are hanging out, dissolved nicely in water. That makes sense because sodium chloride is soluble. And here my silver nitrate are dissolved together as ions, okay? Now when I combine them together, all four of these ions are like, now what do we do? Well, we said the silver and the chloride ions will precipitate, meaning they will combine together and fall down as an ionic network solid, okay? But my sodiums and my nitrates are still like, cool, we don't join together to make something solid. We are still soluble in water. So they're existing as ions. Basically, that means they were hanging out in water before and they still hanging out in water afterwards. This is not chemistry at all. Okay, so only those chloride and silver ions are participating in the chemical reaction, and they form that precipitate. Everything else is just spectatory. And this kind of explains my little cartoon. If you're not part of the solution, meaning you're not dissolved in the water, you are part of the precipitate. And yes, silver chloride, you are the precipitate. You are not the solution. So this is a wonderful, first of all, it was a wonderful review of writing double replacement reactions, reviewing what it's like to read our solubility rules. But now with our understanding of dissociation of ionic compounds, what that means in terms of how these ions exist in solutions and within chemical reactions, to kind of get a net ionic equation to understand some of this chemistry of chemical reactions involved in aqueous solutions.